So far we have only talked about mu as a parameter or as a feature to classify, to do hypothesis testing, right. Remember, mu is one of the statistical parameters and x bar is an estimate of that, but of course what we have learnt is also variance or standard deviation, right. So far we have covered everything about mean, mu and its estimate, x bar. Now we are going to step into doing using sigma squared or variance to do hypothesis testing, okay. So that is actually more important than mean itself, okay. Many a times the feature, the distinguishing feature may not be in the mean, but in the variance of the data, right. In fact, removing mean is a constant common thing, and people today look at only the energy in the signal, how good the energy is, how concentrated or how varied it is. That is nothing but energy, as I told you, is a squared quantity and it is equivalent to the variance in the data, right. And therefore more than mean, variance plays an important role, and that is what now we are going to look at. And the first question comes to mind is, what is the underlying distribution of S squared. Remember, we talked about underlying distribution of x bar, which is using central limit theorem it became to normal distribution, okay. Now we are going to talk about the underlying sampling distribution of S squared. Sampling distribution of S squared, okay. We have talked about sampling distribution of x bar, okay, which in a large population it is simply normal, the assumption of central limit theorem is there, and if it is small population you have to assume that the underlying population is normal and it becomes T distribution, right. Here we have this theorem, very neat theorem, I am not going to prove this, okay. So if x1 to xn is a random sample from a normal distribution, so the underlying population is so if the underlying population is normal, okay, then what with mean, mu and variance sigma squared and S squared be the sample variance, then the random variable chi squared, this is chi squared, is nothing but n minus 1 S squared by sigma squared. In other words, S squared follows chi square distribution, okay. So sum of squared random variables, sum of squared normal random variables follow chi square. Remember what is S squared, how do we calculate S squared? This is nothing but summation of x minus x bar the whole square divided by n minus 1, right. It is estimate of variance, so S squared is nothing but 1 over n minus 1 summation of x minus x bar the whole square. That is what we derived in the, we put it in the class as well, right. I asked you to look at the derivation also, why it is unbiased. So x minus x bar summation of x minus x bar whole square. So what are we saying? Sum of squared, loosely speaking, sum of squared normal RVs follow, random variables follow chi square distribution. With n minus 1 degrees of freedom, because you have used mean mu in your calculation, so with n minus 1 degrees of freedom, DOF. That is the idea. So the sampling distribution of S squared is chi squared, okay, clear. The sampling distribution of x bar is normal, the sampling distribution of S squared is chi squared. Of course a bigger assumption is made, the underlying population is normal, okay, clear. Now once I know this, I can do hypothesis testing, because I can give the confidence intervals, everything, I can start doing hypothesis testing based on sigma squared or S squared. Remember, we are only starting to scratch the surface. At this point, if you have thought about it, you will have multiple questions. In a sense, you are only doing one random variable. How about doing 2? How about doing n random variable, hypothesis on n random variables? Okay, that is how the course will move. So, we are just doing one random variable, the next step will be to 2 and then expand it to n number of random variables. How to do hypothesis testing on n random variables? Using, at that time we will always use variance, we will not even use mean mu, we will use variance. Have you heard of this term called ANOVA? What is the expansion? Analysis of variance, nothing to do with mean. Okay, we will analyze the variance. Clear? So, that is what we will head to. Okay. So, this is the sampling distribution of S squared, and the chi is obviously not a symmetric distribution. By looking at this, you should know it all has a gamma function, etc. This is a gamma function. I do not want you to remember anything. So, this is a gamma function. Do you remember gamma? Gamma function by any chance? What is gamma of n? Okay. So, go check it out. So, it is a gamma distribution, it is a function of gamma distribution, and it is not a squared, it is symmetric distribution. Unlike your mean, unlike your normal distribution or t distribution, this is not a symmetric distribution. Okay, it is a skewed distribution, it can be either on the left or right. So, this is how it will look like. It will have a long tail. Okay. So, this is simple examples of gamma distribution for various k values. Okay, it also depends on the degrees of freedom. So, this is for different k values. Okay. Now, before I conclude the class, the last bit I want to say, we will repeat in the next class. We will also need to give confidence interval for what? Do we give confidence interval for mu or x bar? What did we give confidence interval for? What did we give confidence interval for? Mu lies between x bar plus or minus z alpha by 2, mu equals to. So, what is the confidence interval we are looking? What is confidence about the estimate? Estimate is what I calculate. You always give confidence for the true parameter. So, in this case we have to give confidence interval for sigma squared, right. We gave confidence interval for mu equals to x bar plus or minus z alpha by 2 into sigma over root n. So, now similarly we are going to give confidence interval for sigma squared. Okay. So, sigma squared, what is this? Gamma squared equals to chi square equals to n minus 1 s squared by sigma squared. So, what is the confidence I should give? Sigma squared equals to, sigma squared lies between what? S squared by chi squared at the rate of alpha by 2 and 1 minus alpha. This is not a symmetric distribution. So, you have 1 minus alpha by 2 comma n minus 1, and on the left hand side this should be s squared by chi squared of alpha by 2 comma n minus 1. This is my, and of course the n minus 1 should multiply, the n minus 1 should be multiplying both in the numerator. Understand how did I get? Just rearrange. Sigma squared equals to n minus 1 s squared by chi squared, and one end it should be alpha by 2, the other end it is 1 minus alpha by 2. This is not symmetric. So, you cannot write chi square of minus alpha by 2. Alpha by 2 1 minus alpha by 2. So, the total will be 1 minus alpha percentage confident. So, this is the confidence interval for sigma squared based on your sample distribution, which is s squared. Clear? So, the next class we will talk about chi squared, okay, and then we will finish off chi squared and we will talk about how to test whether the underlying distribution is normal or not. that is called probability plots, and then we will slowly venture into F distribution. Okay.